Okay, so by this point you pretty much know the physical properties of arenes, you know how to name them, and you know the type of reactions that they do as well, and the stability of benzene and why it's stable. What we're going to do today is we're going to look at the reactions of arenes. So that's basically everything with the benzene ring. So that's what we're going to do. So we essentially got three objectives today. So number one is you're going to explain why arenes react by electrophilic substitution. So alkenes react by electrophilic addition, but something with a benzene ring reacts by electrophilic substitution. So we're going to look at why that is. And then we're going to look at the mechanisms of two reactions, which are quite similar, to be honest. The first mechanism is called nitration, and the second mechanism is called acylation. Okay, so that's what we're going to look at. Before we do that though, we're going to look at combustion. Okay, so we're going to look at the combustion of benzene and compare that to the combustion of just a normal alkene. So let's write down the chemical formula of benzene. So benzene is C6H6, right? And it looks like this. So we know that already. Okay. And let's do the same thing, but this time let's compare it to a similar compound. So what looks very similar is cyclohexene. Okay. So cyclohexene is this. Okay. If you work out the number of carbons and hydrogens in that, you'll find it's C6H12. So we can work out the carbon to hydrogen ratio in benzene and cyclohexene. So in benzene, the carbon to hydrogen ratio is 1:1, because a 6:6 ratio is the same as a 1:1 ratio. The carbon to hydrogen ratio in cyclohexene is actually 1:2. So basically, arenes have got more carbon in them than alkenes. And what you find that makes arenes very, very smoky when you burn them. Okay, so arenes burn with a very smoky flame, and that's because they've got lots of carbon in. Alright, so if they burn with a smoky flame, what you would observe is you would observe soot when you burn them. Okay, and that soot is the unburnt carbon remaining. Okay, so we're going to look at some reactions. So the first reaction that we're going to look at is nitration, and the second one we're going to look at is acylation. Let's just look at the reaction in general. So we're used to looking at the structure of benzene like this, okay? Now, an alternative way of drawing that is, if I want to show all the carbons and hydrogens, I might draw something like this. So there we go. So all I've done is I've just copied that really, but put the carbons and hydrogens in there as well to show you what happens. Now, arenes always undergo electrophilic substitution reactions. So if you ask what type of mechanism a compound containing a benzene ring does, then the answer is always electrophilic substitution. Okay, let's have a look at how that happens then. So if I write down the symbol of an electrophile, and if I just have a generic electrophile, I could put the symbol EL positive like that. Okay, so that shows that it's an electrophile. Now the word electrophile means electron seeking. Now the electron density in this case is in the benzene ring. So the electrophile seeks out the electron density in the benzene ring. So remember, when we draw curly arrows, the curly arrow always comes from the area of electron density, just like it does when an alkene reacts with bromine, for example. Here, the electron density comes from a ring, because that's where the electron density is. And we have a curly arrow that goes from the ring to the electrophile. Now, this is the first sort of curly arrow that we've seen so far in A-level chemistry that comes from a ring. It doesn't come from a particular bond, but because remember that electron density is delocalized. So let's draw what happens here after the first step in this mechanism. So all of the carbon atoms are still chemically bonded together. All of these hydrogen atoms are still intact. We haven't done anything to those. But what we've done here now is we've broken the aromatic ring because we've used some of that electron density for the reaction. So we need to reflect that in our mechanism. And in doing that, what we do is, instead of drawing the electron density all the way around there like that, to show there's a delocalized ring there, then we show a break in it. And the curly arrow comes from between these two carbons here, so we show a break in electron density between those two carbons there, like that. So we draw the ring like this instead. Now, what I've done here is I've put the electrophile onto that carbon there. Often what you can do, you don't have to, what you can do, and I find this much more useful, I mentioned this before when we do mechanisms, is to do a dotted line between the bond that you're gonna make between that carbon there and that electrophile. So that's a new bond between that carbon there, which is this one here, and this electrophile. Now remember, the curly arrow is going away from this area here. So we're taking electrons away. Because I'm taking electrons away from this area here, that leaves this area with a positive charge. So we just write a plus actually in the centre of the ring. Because that positive isn't really on a particular carbon, it's just at the centre of the ring there. Okay, now the next thing which happens is that aromatic ring system ends up being reformed. So I've broken it here. I'm going to reform this aromatic ring system now to give it back its stability. So it's the electrons from this carbon here and that hydrogen there. So it's the electrons between that carbon and that hydrogen which reforms that aromatic ring system again to give that delocalized ring system. That's what I'm going to do. I'm going to draw a curly arrow from that bond there to that gap in that ring there. So from this bond to that gap in the ring. So it always goes from the carbon hydrogen where you've put the electrophile on. So curly arrow from the middle of that bond to the ring system there. Let's draw the product. So I've reformed this ring system now with those electrons. So you draw a complete circle there. Because I've put the electrons back onto that positive charge, I've now neutralised that positive charge, so I don't show a positive charge here. I'm going to draw in this hydrogen, that one, that one, that one, and that one, and that electrophile attached to that carbon there. Represented by EL there. Now, I've broken this bond in this particular step here. I've taken electrons away from that hydrogen there. I've taken them away from that hydrogen. Therefore, that hydrogen there becomes positive, and I've broken that bond. So I write plus H plus. So I've lost a proton. That's what I've done there. That is a proton, remember. And H plus is a proton. So this is the overall reaction. The two that we look at are nitration and acylation. But in general, they kind of form this general idea. So the first thing we're going to do is we're going to look at nitration. So nitration is the substitution of an NO2 group for one of the hydrogen atoms. So it's a substitution of an NO2 for an H. That's what we're going to do. So let's have a look at the first step. Okay. In the first step, what we do is we mix concentrated nitric acid with concentrated sulfuric acid. That's our first step. Let's write down the chemical formula for sulfuric acid and the chemical formula for nitric acid. Okay, now here we've got an acid reacting with an acid. That is actually possible. And that is possible because sulfuric acid is a stronger acid than nitric acid. So you need to remember that sulfuric acid is a stronger acid than nitric acid. The easiest way to remember that is because it's got two protons there. If you've already studied acids and bases, then you'd know that this is a stronger acid than nitric acid. So because this is a stronger acid, the sulfuric acid here acts as a Bronsted-Lowry acid. And you learn about Bronsted-Lowry acids in the acids and bases topic. So a Bronsted-Lowry acid is just a proton donor. That acts as a Bronsted-Lowry acid, and the nitric acid here acts as a Bronsted-Lowry base. These are two people's names, Bronsted and Lowry. It's not an English name, this. It's got its O with this funny line through there. So remember, a Bronsted-Lowry acid is a proton donor, and a Bronsted-Lowry base is a proton acceptor. So what happens is the sulfuric acid donates a proton to the nitric acid. So it donates a proton from the sulfuric acid to the nitric acid. That's an H plus, remember, a proton. So what we get is, if we remove the proton from this formula here, we get this structure. If nitric acid has gained a proton, we get this structure. Okay, right. Then what happens is, this structure here, I'll rewrite it down here. So this is basically, it's nitric acid with an extra proton. It loses a molecule of water. So it loses a molecule of water to make something. I'm going to look at that something in a second. So it loses a molecule of water. So I'll write that down as a sentence. Now if it loses a molecule of water, we can work out the chemical formula of this to balance the equation. And we get this formula here. That's NO2+. Now NO2+ is called the nitronium ion. And it's got an other name as well. And the other name is called a nitrile cation. And that is your electrophile in the next bit of the reaction. So we've actually generated the electrophile. So I haven't even seen a benzene ring yet in this particular chemical reaction. Okay, so what we're going to do now is we're going to take this very reactive nitronium ion and react it with our benzene ring. Let's have a look at our generic mechanism before we do that. What we've got here is we've got electron density coming from the delocalized ring system to the electrophile. So in this case, the nitronium ion is the electrophile, and the electron density goes from the ring system to the electrophile. Do make sure that when you're doing this mechanism, it's not always clear in textbooks and things, you must make it clear in your exam that your curly arrow goes from the ring system to the nitrogen. So I've now broken the delocalized ring system between that carbon there and that carbon there. And electron density has come away from the ring system, therefore it has a positive charge. Now what I've done here is I've drawn that hydrogen in there. I've not added a hydrogen because it was still here. It was still there. The hydrogen was still here. But I've now drawn it in because I'm going to use it in my mechanism. So remember when you're drawing skeletal diagrams, you don't have to show your hydrogen atoms. But obviously if the hydrogen atom is involved in the mechanism, and in today's lesson they are involved in the mechanism, at that particular step you need to draw it in. So what we do now is we reform the delocalized ring system between that carbon there and that hydrogen there. That's where we start the curly arrow, and it finishes up by reforming the ring system there. So we've got a complete circle there. The NO2 group that I've added, and because I've taken electrons away from this hydrogen, I get an H plus here, like that. Okay, now, the H plus is a reactive species. That isn't just going to hang around there. Let's go back to see what we didn't use. Now we know that this species here went on to make NO2 plus in water. We know that the NO2 plus was used here. Water is a stable molecule, so that is going to be a product. So I'm going to write down the overall reaction here. So start off with my structure with the benzene ring in it. And I know that I'm going to make water as one of my products because the water isn't involved in the mechanism at all. It appears here as a product, and we don't use it in this step here. Therefore, water must be in the overall mechanism. Remember, this is overall. It's overall reaction. The mechanism is above. We've now nitrated this benzene ring. So that is a product there. And what happens is, can you see this structure up here? This HSO4 minus. This HSO4 minus up here is produced in this step. It isn't used in this step. It isn't used in this step. But what happens is, the H plus, which is produced in the final step of the mechanism, reacts with this HSO4 minus. So H plus here reacts with the HSO4 minus. If we take an H plus and react it with HSO4 minus, we get H2SO4, which should ring a bell because we started off with H2SO4 here. So essentially what's happened is, it's regenerated the H2SO4. Because it's regenerated the H2SO4, we say that the sulfuric acid, the H2SO4, acts as a catalyst. So that is actually acting as a catalyst. Because it's acting as a catalyst, we write it on top of this arrow here. It's neither a reactant, it's neither a product, it's a catalyst, so we'll write it on the top of the arrow there. The nitric acid, which acts as a bronze auxiliary base, gets used up. Therefore, that is a reactant. So this is the overall reaction. You've got your arene there, in this particular case we've just drawn benzene, nitric acid, sulfuric acid catalyst, nitroarene, and water. So water is your byproduct. Alright? So that's our mechanism. In general, what we've got here is we are generating the electrophile in two steps. This one and this one. And the water is a byproduct. And then you've got a two-step mechanism involved in the arene. The first step is the electrophile being attacked by the delocalized ring system. And the second step is the removal of a proton from the structure. The final step is the proton removed from the structure reacting with the HSO4 minus that was produced in the first step to regenerate the catalyst. Overall, this is the reaction. So this is nitration of an arene. Okay, we're going to look at the next type of mechanism now. So we've done nitration, let's tick that off. We're now going to look at acylation. Now there's another name for acylation, okay? And the other name is Friedel-Crafts. So whenever you see the word Friedel-Crafts written down, it means the same thing. Sometimes you call it Friedel-Crafts acylation, okay? And it's named after two chemists called Charles Friedel and James Crafts, who came up with this mechanism, okay? So again, it's an electrophilic substitution reaction, this particular action. So what we're going to do is we're going to do this particular reaction as well. So the first step is to generate the electrophile, just like we've done here. So the first step is to take your aluminium chloride and react that. Okay, so let's look at acylation, which is Friedel Crafts now. So what we're going to do now is we're going to take a compound, and I'm going to write this compound down like this: RCOCl, which can be written like this instead if you want. R, single bond C, double bond O, and then Cl. So you'll probably recognise it like this more. But when you're writing mechanisms down, sometimes it's easier just to write it like this to simplify it. Okay? And we take this and we react that with aluminium chloride. So we add that to aluminium chloride. Now aluminium is in group 3 of the periodic table. So it's aluminium 3+. Therefore the chemical form of aluminium chloride is AlCl3. So what happens is the AlCl3 removes this chlorine here. If it removes this chlorine here, you get AlCl4-, like that. If that's got a minus charge, then this species produced here is going to be positively charged. So it's RCO+, like that. If you were to draw it, it would be RCO with a positive charge here. So this could be anything. For example, it could be CH3COCl, which would make CH3CO positive. Or it could be something like this, with a slightly longer chain, but it's the same principle. And what we've done here is we've made the very reactive electrophile. So this is your electrophile. So what I've done here in the first step is I've generated the electrophile. This is what we're going to put on the benzene ring. Let's have a go at the mechanism then. So I have our benzene ring here and our electrophile. What I've done this time is I've drawn it this way on, like that, rather than like that, because I know that this is my source of electron density and I need that next to the positive charge there. So again, like I did last time, a curly arrow from the delocalized ring system to the electrophile, like that. Because I've disturbed this delocalized ring system here between that carbon and that carbon there, then I draw a break in the circle here. And I put a positive charge there because I've taken electron density away from the arene in the middle there. And I formed a new bond between that carbon there and that carbon. So this time I formed a carbon-carbon bond. Previously, I'd formed a carbon-nitrogen bond. So I have a carbon-carbon bond formed. This hydrogen that comes off here was already here at the start, but now I'm going to draw it in because I'm going to use it in my mechanism. I use those electrons between that carbon there and that hydrogen there to reform that benzene ring. And I've taken electron density away from that carbon there, so I get an H+. Just like I did over here. Okay? And remember the H+ reacted with the HSO4- to regenerate the catalyst. Do exactly the same thing here. So I've made this H+ here, and because it's got a positive charge, it isn't just going to sit there, it's going to do something. It's going to react with something which has got a negative charge. Let's look back. Within the very, very first step, we produce this AlCl4-. So the AlCl4-, because it's got a negative charge, is going to react with that H+ there. And what it does, it regenerates the AlCl3, which I started off with. Therefore, the AlCl3, just like the H2SO4, acts as a catalyst. And I've made HCl, which is a byproduct. So in the nitration reaction, the byproduct was H2O, but in the acylation reaction, the byproduct is HCl. In the acylation reaction, the catalyst is AlCl3. In the nitration reaction, the catalyst is H2SO4. So there are similarities there, and the mechanism is more or less the same thing. It's the same idea. So let's write down the overall reaction for this. So we've got an arene, an acyl chloride, aluminium chloride catalyst, HCl byproduct, and we need a name for this. So we've got an arene bit, yeah, and we've kind of substituted hydrogen for this acyl group, okay? So this is what we call an acyl group. That's because it's come from an acyl chloride. So that is an acyl chloride, therefore that is an acyl group. This is what we call an acyl ion. Now, if this is an arene, and that is an acyl group substituted, then we'll call this a substituted acyl arene, or an acyl substituted arene. So that is an acyl substituted arene. That's our product. Okay, so that's how you would do that. So let's do an example. So for example, e.g., if you've got something like benzene. So benzene, we have an acyl chloride. So let's name this. This has got 2 carbons. So this would be ethanol chloride. And we take our aluminium chloride catalyst. So we'll have an acylation reaction here to make this compound. And HCl, okay? So that's an example of this type of reaction here. Just out of interest, this one. So we could do an example of nitration. Now nitration of benzene and arenes is very important. So you need to know some uses of nitration reactions. So we're going to look at that now. So I think the most easy one to remember is that nitration is an important step in the production of explosives like TNT, okay? So we'll look at what TNT stands for in a second. I'm going to show you a structure here. First of all, this is not TNT. This is obviously methyl benzene. So before chemists started to name compounds using our standard naming system, this was given the word toluene, okay? Spelled that wrong there, do apologise. That's it. That's toluene, or methylbenzene, it's the same thing. That's just an old-fashioned name, okay? TNT stands for trinitrotoluene, or I should say 2,4,6 trinitrotoluene to be precise. So if toluene is that, then 2,4,6 trinitro means I have nitro groups on carbons 2, 4 and 6. Well, that must be carbon 1 because it's based on toluene, so that has to be carbon 1. So on carbon 2, carbon 4 and on carbon 6 you've got nitro groups. That there is 2,4,6 trinitrotoluene, which is TNT. Okay, that's the chemical formula of TNT. All right, now the way TNT works is it works in two ways. Okay, the first way is that it's very exothermic. So if you were to look at the reaction, look at the bond enthalpies before and after the reactions, you would see that it's a very, very exothermic reaction. And the second reason why this basically works as a bond is that it produces a lot of gas. And we see that when we write down the balanced symbol equation. So let's have a go at writing down the balanced symbol equation. So we have toluene here with those 3 nitro groups on there to make trinitrotoluene. And that's actually a solid. It's actually a low melting point solid. And if we react that with oxygen, you actually need quite a lot. It's actually 10.5 moles of oxygen for every molecule of TNT you've got. And that produces a load of gas. So it produces carbon dioxide gas, nitrogen gas, and steam as well. Because remember, this can produce at a very high temperature because it's already exothermic. So you don't get water produced, you get steam produced. All right? And you get loads of this gas. 14, balance this equation, you can work it out. 14 moles of that, 3 moles of that, and 5 moles of that. You don't need to know this reaction, by the way. You don't need to know it. But you do need to know the use of nitrate and arenes, and this is one of them to produce explosives. So what we've got here is got a load of gas produced, and it's very exothermic. These two things make TNT a great explosive. Okay, so that is basically the reactions of arenes.